And thank you very much for the organizer to inviting me to here and to organize this very nice workshop. And I really enjoying that exchange with a lot of people here. So it's a very great opportunity. And yeah, very happy today to talk about our recent research. So this is a continuous effort with my collaborators at, so first from Imperial College London and the UK Lemmenholm Wildfire Center, where I did my postdoc, and also with my current colleagues and some students at NPC. So actually things since last year. Okay, so here's a simple outline of my presentation. So at the beginning, I would like to give a very brief introduction to the method of machine learning and physics or empirical model for wildfire predictions. I think it's a perfect time to do that and actually learn a lot during the past 2 or 3 days and actually update quite a lot my slides. Okay, and for the main part of my talk, I'd like to talk about our recent open access package called PyTorchFire. So PyTorch is the mainstream framework to train the neural networks, but PyTorchFire actually is a cellular automata model. Okay, so the idea is we want to write a physics-based model on PyTorch. So in that case, we can have first the GPU acceleration and secondly the differentiability, and we'll see how we're going to be able to do that. And I would like also to talk about a generative AI model, namely a diffusion-based model for the ensemble prediction of the wildfires, because we know wildfires, they're quite stochastic. I think we have already had this discussion about how to have a good perturbation, to have an ensemble prediction to cover all the possible scenarios. And if time permits, I would like also to talk about the work of hybrid data assimilation and machine learning algorithms, which is also my main direction of researchers, in particular of our open access TorchDA package. So the idea is also to do data assimilation in the PyTorch. So in that case, you gain an end-to-end differentiability and everything can be done in a unified framework. Okay, to start with, here I simply present the simple algorithm, which is also very classic from Alexandre Didas. So this is a cellular automata empirical wildfire model. So the idea is very simple and it's quite similar to what our lovely colleagues have presented for the propagator. And I think actually it's the algorithm that used in the first version of propagator. And I will give more details since our PyTorchFire is actually for now based on this simple algorithm. I've seen that there are so many different physics or empirical-based models. They have shown their efficiency in different operational scenarios. But overall, we think there are still some difficulties. So the first is about the non-differentiability. So here I mean the differentiability regarding the model parameters and the possible human interventions. That will give more details later. And for the second point, that's actually easier to understand. Since this model, they're not written in PyTorch or in JAX. So if you would like to couple this model with currently large AI weather predictive model, they're now becoming the reference in the field. You can only do that in a quite rigid way, which means, of course, you can get the output from the weather model and you put that plug into your fire model and you can do vice versa to have the model coupling. But since they're not in the same framework, so you'll not be able to share the gradients, you'll not be able to do some core fine-tuning together, so there still might be some limitations here. Okay, so come back to the first point about the differentiability. So we know that usually empirical wildfire models, they depend on some parameters, so that actually also includes neural network-based models. And typically, we know that wildfire are quite difficult to be predicted and they're quite stochastic. So usually this model needs some calibration in different ecoregions or even sometimes at different fire events. Okay, so if the model is not differentiable, of course you still have ways to do that, and this is usually based on what we call the sampling methods. The idea is you're going to try to generate different scenarios and try to approximate the gradient of the model because you don't get it directly by the differentiability. Okay, so basically you try different scenarios, see, okay, here I have a better fit, so I'll continue on that directions. Okay, so here is like one of the paper that do these methods. And the other thing is, for example, as I think our colleagues, Nicolo has also mentioned, the firefighting is possible with the cellular automata model, but also on other physics-based or neural network-based models. If you want to choose the best fire fighting actions, for example, the the flight to drop the fire retardant. If the model is differentiable, it'll be so helpful because in this case, you can simply define, for example, I want to minimize the final burn area, or I want to protect some urban area as high important area. So in that case, you simply calculate the derivative of your function of the final burn area, and you probably get that. Otherwise, current method used, for example, like reinforcement learning, etc., to do this. This also the idea is that you try to explore all the possibility in the space. Okay, so you need to do a lot of samplings, somehow try to find the best strategy. And even in the case if your derivative is not stable, it's still going to be very helpful because what you can do is you can combine these two methods. You're going to do the sampling alongside the derivative, which told you they're going to reduce the burn area. Okay, so even in this case, your derivative function is not stable, it can somehow still guide you for the sampling and it will be more efficient for potential firefighting strategies. Okay, so here I talk about the 2 points, and of course there comes the machine learning models. And we have seen, of course, so many these past 2-3 days, and typically these kind of methods, you take the previous wildfire mask or burning area, and you try to predict the next frames, okay, or the next several frames. And you can give all the weather or the geological features as input of your model. There's so many ways to do that. We have seen like pixel-wise spatial temporal models, like LSTM and reduced order models, etc. So of course, I take the advantage to promote some of my previous work, but there are so many in the domain, and a lot of them are very good. Okay, so of course here with neural network, you know these are auto-differentiable. Okay, and they're quite fast in inference, and you can easily couple that with large weather AI model. But there still might be some drawbacks that needs attention. So here, as I list, what I write in the red part, I think, is something quite specific to wildfire, which usually we do not share, for example, with other geoscience model or with other weather predictive model. So for example, about the generalizability, that when you change the ecoregion, if you want to predict how fire spread, the transfer learning can be quite difficult, as Jonathan mentioned today. And also another specific thing is wildfire are so heterogeneous in terms of scales. Okay, so you get very large wildfires that contain a lot of pixels, where you have very small wildfires, and that usually dominate your data set. So if you train the neural network, sometimes you find that the training will be overfitting on the small wildfires. It will try to predict you that nothing happens, because in that case, you're using MSE loss, and it's the most safe way to get a low MSE loss. He will not predict the extreme cases, but in the wildfire, actually it's the extreme cases which are more interesting and important to us. Okay, and also for the leg of probabilistic prediction, that's somehow like the same. If you use a MSE type of loss, like a deterministic prediction, the model will tell you in average what is the best solution. Okay, so in average, this is what happened. But again, what we are interested in is mostly the worst case. Okay, or we like to know the whole probability of what's going to happen after. And again, the poor explainability, that's a shared challenge with different models. But in wildfire, typically you need to do like model calibration or active learning or fine-tuning, whatever you call that. It's true that neural network, they are differentiable, so that helps. But neural network, you have so many parameters, okay? And if you need to retrain your model every time like you get the new observations comes in, and you have to make sure that these training converge. So I'm not sure at the end it is winning, because it's still very, very time-consuming to retrain or to fine-tune your model for to calibrate in new wildfires. So here comes our idea. So actually what we want to do is to write equation-given or like physics or expandable models using PyTorch. Okay, you can try PyTorch or JAX. Here we choose PyTorch. And why would like to do that? So first you will get the GPU acceleration thanks to the CUDA ecosystem, which is quite friendly to the PyTorch functions. And secondly, it's about the differentiability. So of course, this is not automatic. A function is not differentiable. You rewrite that in PyTorch will not be differentiable as well. But there's so many engineering ideas, so many packages and tools have been developed to help the optimization of the neural networks. And actually, we can make use of these tools. Okay, we can make use of these tools to help improve the physics-based model. So that's our idea. And at the end, of course, with the AI weather modeling, that you can have the end-to-end differentiability, and you can fine-tune the models together. So this is our idea. And as I mentioned, so we start actually to work that about several months, less than a year. So we start with taking a quite simple model, which is the cellular automata of the Alexandridas. So we know very well this cellular automata is piecewise, so it's not by definition differentiable model. Okay? And actually in this model, it depends on several different parameters. As you can see here, so C1, C2 decide how the wind impact, and also you have the R decide the slope, the elevation impact the fire, and you have the P continue and the pH. So 5 parameters. And we will not touch the P vegetation and P density. So these are in the lookup tables as presented by Nicolo and his colleague. So that's quite similar. Okay. So of course you can read that in PyTorch. Now the question is how you're going to be able to make that differentiable. The idea actually is quite straightforward. So when you simulate the fire, of course, if you take only one scenario, it's not differentiable because it's stochastic. From the previous step, you rerun several times, you'll get different things. So the whole idea is to calculate the probability of the cell could be burned. Okay? And this is actually very simple because one cell could be burned only by taking, since here is not considering the fire spotting phenomenon, so can only be burned by the 8 directions that you can see here. So if you give the previous burn area, you give the parameters fixed, you give all the climate condition, wind conditions fixed, and you calculate the next level probability. And of course, since it's a probability, it's differentiable compared to your parameters. And what you can do is you can do an autoregressive computing in this case. So you know the next step probability, and you continue to do that, you will get, again, the next level probability on top of that. Okay, so for the next step, you can simply write a very simple equation to do that. Okay, so that's what you're going to get. So from here, you can have somehow like a prediction of the probability of the cells could be burned after several time steps. And now the question is how we're going to compare that against the satellite or the observation, because what you want is to minimize this difference. This is your objective function. Okay, so here is what you observed. And easiest way you may say, okay, I know which area has been burned before and I observe the burn area currently, so I will just compute that on whole image, but you will have a lot of cells to compare in this case, to compare the probability, and even your function is differentiable, it will not be very optimized to do that. So here our idea is to define what we call the step rings. So the idea is we only look at the fire frontiers, okay, of your observation. So in that case, if from a probability point of view, you will have 100% that's burned because you only have one realization of your probability. And what we take is also the layer outside of that, okay? The reason is you can not only take the burn area. If you take the burn area, it's like you train a neural network. It will predict everything has been burned, because it's easiest for him, so he will just get the good results. So you have somehow to keep an equilibrium between burned and not burned cells. So that's what we decide, we call that step rings. And now the idea is how we're going to be able to compute the loss between what you predict and what you observed. So since this is like a binary problem for each cell, so we can simply use what's called the binary classification entropy existing and use a lot in wildfire models. Okay, so the idea is for each cell that's on these step rings, we're going to calculate the binary classification entropy. Okay, that's the typical loss after what we call the softmax layer. It's like you predict, neural network predict if it's a dog or it's a cat. Okay, here is predict if it's burned or not, but you kind of sum that on all the 5 frontiers. Okay. And here, we still want some control to say the total burn area. We want the total burn area to match. And we do that with the average pooling. The idea is that we have the whole map here, okay? So I know this part as 200 cells been burned, this part 10, this part 300. And by changing this parameter, you can somehow cover the different area of your map. And this is the idea, so somehow to find equivalence between the exact point on 5 frontiers and the total burn area. So yeah, we have this package. So the first version of the PyTorchFire is published, and we also have our packaged modular for that you can do with pipe install directly on Python. And it supports both, of course, GPU and CPU implementation. And here, as you can see, for the parameter calibration, here you start with your initial guess of your parameters. Okay, and then we provide the examples that's right on Google Colab that you can directly run that on Colab. And in this case, so your oscillator that we actually give a lot of observations with synthetic data, so you can actually choose the observation frequency. So how many steps that between the two different observations. Okay, so that means your model have to be propagated a lot of times until next time you see the observation. And the probability calibration is whole or embedded, so it's only one line of code. And what you can do, for example, is you train your model with the first 50 time steps. Okay, you calibrate, you assume that now with the first 50 time step, I have all the observations. And once the model is calibrated, I can run for the last long prediction until long time after. Okay, so this is some examples that we have been shown that in the paper. So these are real wildfire for the biofire in California. So we typically try to have some dummy parameters to start with. Okay, so at the beginning, you can see here the first line here, the first column here, that it's completely underestimate your burn area. Okay, and the third column here is completely overestimate. Okay, and in both cases, after calibration, of course, we don't get a perfect match with the observations, but you can see here is way close. Okay, towards the end. And for this data, it's the modest wildfire product, and we only have the daily observed burn area available, but we also provide in the notebook that the examples that you can do the calibration with another simulation. Okay, the idea is if you start here, you can see the fire will probably stop because it's too small, like the probability you calculated. And if you run the simulations, this example I showed in the previous slide with 50 time steps, but interval is 10. So actually you have 5 observations. And this is on one single GPU, it's about 5 or 6 seconds to do that, to do the calibration. And then you can run that for later predictions. You can see it's not that bad, okay? So of course, you're limited by the degree of the freedom. You will not be able to have a perfect match, but it's somehow much better than the non-calibrated one. And in terms of the computational efficiency, so we have compared that with an MPI on CPU on 64 core for the NumPy version of the same code. And we can say our PyTorchFire code is slightly better than the NumPy version. Well, if you pause on the GPU, that's really you see the differences. Okay, so the two different type of GPU. The first one is almost on desktop that you can have. Okay, yeah. So that's the idea. And continuing to this is for the INR OFML project. What we want really to do for the next step is we want, as I mentioned, to make the fire break or the fire retardant placement to make that differentiable and use that to do the optimization of the strategy to fight against these fires. Okay, there already exists a simulation on CA automata that modelize this fire retardant job and its effect. But our idea is to make that differentiable. So we haven't done that yet, but that's our objective. Okay, so now I probably pause on the second part is about the diffusion-based generative AI model for the ensemble fire predictions. So the whole idea, as I mentioned before, is to say, okay, given the same input condition, given the same fire burn area, actually, we would like to represent somehow a probability of fire spread for the next steps. Okay, so that's, in this case, translated by an ensemble of predictions. But how are we going to be able to do that? If you change like the input, that's one way you change the input condition to do that. But you need to know how to appropriate add the perturbation. So for example, in a case like dynamical system, people do ensemble Kalman feature. Usually you will rely on a very long uncertainty propagation to say that, okay, at the end, this uncertainty is the uncertainty of the model. But of course, here we don't have that, okay? And their work has already been doing that, for example, in a Jamcast for numerical weather predictions. And here we are in a specific case. So quite similar to what Jean-Baptiste present this morning, that we're trying to do emulator for the CA-based model. And the difference here is the CA model itself is stochastic. Okay, so it'll give you also an ensemble of predictions, a probability of predictions that you can calculate or you can estimate it, as our colleagues has done yesterday by an ensemble run. So if we use the generative model, diffusion model to learn that, the idea is to say, okay, I will have a way to actually examine the output of my model to see if it's really captured the real stochasticity of the wildfire, because here is on simulation, so I know that. What if you do on the weather? Somehow people try to prove that through using different approaches, but there's no way to say, okay, this is exactly the stochasticity, because you don't know how random it is. Okay, so here I will try to do our to do a brief introduction about how the diffusion model works. So here, first start with the unconditional diffusion model. So we know that diffusion model has been proposed at the beginning is to generate the data, okay? So Holman has presented the picture of the dog, so I take the same examples. So imagine that you have a lot of dogs, okay? A lot of pictures of dogs, okay? And you want to generate a new one. So since you have millions of pictures, what you're gonna do, one of the naive way is to say, okay, I will get all these pictures, I will try to transform somehow to a latent space or to some probability space, and we'll try to smooth out between the different pictures, okay? So in that case, I get somehow like a probability density function of all the pictures of the dogs. And now you ask me to generate a new picture, okay, I will just find a point in that space that's not from the given data. So I will generate a new one to you and say, okay, this is a new dog. But if you think about that, what you do is in some sense like doing interpolation of pictures of the dogs, okay? 2 dogs or several dogs. And you could imagine this will not be very realistic. You will not get a realistic new dog just because you do the interpolation, because actually that's because the probability density function is too complex. What you see is you have 2 pics here, 2 images here. So what you assume is, okay, this is quite smooth between them, but you never know what's in between. No matter how close they are, you never know in between what happens, and it's usually quite chaotic. So what's proposed by Song et al. in this classical and seminar work is to say we are going to transform this probability density function to something quite smooth, quite well known, and typically a Gaussian distribution. And the way that they try to do that is to add noise gradually until the end that you get a totally Gaussian distribution, so a totally noise, okay? So that's what we call the forward pass is in this direction, okay? From the distribution, you add gradually the noise until the end, and you get a total noise. Why you cannot add noise directly to the end is because if you dominate your original distribution by some other distribution, by the Gaussian distribution, you will never know what's the original look like. You will not be able to go back. We want each step to be trackable, okay? So in that case, it's approximately inversible, and that's the reason why you need to go that gradually. Okay, so when we say we train a diffusion model, what actually you're doing is you start from the total noise, okay? You do some sampling, and then you try to denoise that. So the neural network is used to go back, okay? So you go step by step. You go, the first step is purely noise, and then the second step will be something a little bit less noisy, and then you go back to back until you come back to the original distribution. Okay, so that's the idea. And the advantage of doing that, you can really see this as making a bridge between the very complex distribution to our very simple Gaussian distribution. So now if you ask me to generate a new dog, I will do the sample directly on the Gaussian distribution, okay? And then I just denoise that back to the original distribution, and then I will give a more realistic dog, okay? And I know dog and wildfire, they're not exactly similar, but if we make analogy, and that's people do, for example, in weather prediction, that's kind of this idea, but you're doing a conditional prediction, which means at every step, when you denoise back, you give somehow the previous, for example, the previous burn area, the previous the current meteorological condition to say, this is the fire today. Based on this, generate me a possible scenario, what happens tomorrow, okay? And you can do that by sample a lot of points in the original Gaussian distribution, and you will have an ensemble of prediction on the output. And by doing that, actually, you don't need to do any perturbation of the input yourself. Okay, so this is the idea, and this is the idea of people doing the weather predictions, and we try to use the same ideas for the ensemble prediction for the wildfire. So yeah, this I think pretty much I've explained how these things works. So here you have different fire images, and you take each column. Actually, these are different generation of the next day wildfire, and you can somehow find at the end like an ensemble of all the predictions. So for example, since it's binary images, you can take the average to say, okay, this is somehow I know the probability of each cell going to be burnt in the two-dimensional space. So in this simple case. Okay. So remember I've mentioned here we have a unique advantage is because itself is a stochastic code. When I train this, actually no, it's not me. So when we train this neural network, we never tell you what's exactly uncertainty at each cell. Okay, we just give you one pair of input and it will be one pair of output. So it's to let the neural network to learn what is the probability. So here what you can see here on the left side is the diffusion model, on the right side is the CA model. So since it's an emulator here, so actually we assume that we know the ground truth. And as you can see, we're overall quite clever. So no, not clever, sorry, we're quite happy. It's the end of the day, apologize. We're quite happy, despite we know it's a quite simple, like scenarios here, we always stay in the same ecoregion, so it's more like a profile concept. But as you can see at the end, we kind of managed to have a good prediction of the probability of fire burn in the following steps. Okay, so another thing I haven't mentioned before is diffusion model is a way to train your neural network. So this is against deterministic training using, for example, MSE for training your neural network. Also, you can also use MSE for diffusion model, but that's the other thing. So I don't want to get too far about that. But there's another term that could play is the exact neural network structure. What neural network you're going to use to train this diffusion model. So that's initially start with UNet, and then people start, of course, add attention mechanism to the transformer, etc. So here we compare simply 3 different structures, and it's also we want to make sure and to show the reviewer that it's not just a chance that we get that. Okay, we actually can get quite stable results. So we have the UNet with attention, we have the UNet without, and we have a simple ResNet-based convolutional autoencoder. Okay, and what you observe first here is like you have this very large arrow bar for degree, okay, which is the simple autoencoder. So that actually means the structure still matters when you train a diffusion model. So in this case, simply means it's not converged. Okay, so you're training the not converge. Well, we can see the UNet with attention and the basic UNet will have a much better result compared to the simple convolutional autoencoder. But what's more important is actually to look at the difference between the full color and the dashed color. Okay, so if you compare them in all of these different metrics, especially in the MSE, you can see that in each of these pairs, except in the case that the convolutional autoencoder that do not converge when you train that with diffusion model, in all the other cases, we are always better by using these ensemble predictions. And what we do is to have an ensemble prediction, we take the average and we compare against the ground truth, which is the CA. Okay? But this average is different from you learn the average using like a deterministic neural network. So probably I'm not going to the details, but if you have questions, we can talk about that later. Okay? And it shows that in all 3 structures, we always have these quite consistent advantages, and it really shows the advantage of using these probabilistic prediction methods. Okay, so our idea also in this ANAP project is try to couple that with the Felix-based model, and this is also linked to what Holman proposed, I think, this morning to Jonathan, is to use the neural network to learn the residual of the Felix-based model. And on top of that, since we have both writing in PyTorch, actually they can share the gradients. We can also have the possibility to fine-tune both at the same time. So we don't know yet how we're going to do that. Okay, what time is that? Okay, I think I talked about 30 minutes, so still probably some small time. So I just want to talk something about also data representation and machine learning. So I heard there's fantastic talks about data assimilation, so today by Jean-Christophe, and yesterday by Melanie. So I would assume that this is also very, of course, useful for people working in geoscience. So here I show a simple case that we have in Ile-de-France, where we have the observation of different the concentration of the different air pollution, like the including NO2, O3, PM10, PM2.5, etc. So different pollutants will have different number of observations. And the whole idea is either you're going to reconstruct your full field from these observed points, or is you have some algorithm either based on machine learning or based on like typically software-based, physics-based models. You give you some prediction and you can make the correction from these very sparse observation points, okay? So we want to have this core assimilation system, which means in the NO2 you can see you have way more observation points, while in PM2.5 and PM10 you have way less. That is, there exists this underlying correlation of different pollutants, and that's also the truth in a lot of different geoscience problems. So we want to use the fact that we have more observation of NO2 to correct for example, the less observed PM2.5, PM10, etc. And of course, we want that to be efficient. So I will not go to too many details here, but if you want to do data assimilation, that's what Air actually they're currently doing in the full physical space. There are several problems. First is the state space is quite large. Okay, imagine you have 1,000 times 1,000, you have 1 million points to be corrected. And also, so you observe some values here, you want to correct the original prediction. So you don't want only to correct one point, okay? You want that knowledge to be diffused spatially in the two-dimensional space. And in data assimilation, this can only be done using the error covariance matrices. Okay, so I have a huge error covariance matrices, and how you're going to estimate that is even a problem. First is because high dimensionality, and secondly, these error covariance matrices represent the covariance of the errors, not the covariance of the values. So how you're going to have a proper way to estimate that is actually a challenging thing. So I spent all my PhD studies on that. And unfortunately, without deep learning, I don't find anything super interesting. That's not what I said the day of my PhD defense, of course. But anyway, so here we try to propose another family of the method. It's called latent data assimilation. So somehow it's also linked to, I guess, what Holman you present, is to have a low dimensional representation of the physics quantities, okay? So instead of correct original image, we're going to simply correct the low dimensional representation. And the advantage of doing that, first you get a low dimensional problem, so that's faster. And secondly, since you do the data compression, you somehow take into account all these correlation at different species and at different spatial and temporal spaces. When you correct one thing, when you correct the latent vector that represent the whole physics system, you're not going to correct one point, okay? You actually correct all the points that's correlated to that. So that's the main idea. And you can simply write here, it's a 3D function, but you can use 4D var if you have several time steps. You can use ensemble common feature to do that. And there are several actually contributions. That's something I've been working on during my whole postdoc. But there are also other people like propose different structures, how to optimize the encoder-decoder, how to optimize the latent space representation. So in that case, you will have a better assimilation results. Okay, so yeah, why didn't change? Okay, so one last thing is more or less like engineering problem, is just to say, since we would like to provide some benefits to the community of the scientific community, and for people, for example, originally use Python to code that their open access packages like RDAO or OpenDA to perform data assimilation, but they do not support the neural network as transformation functions. Okay, so if I permit to make another link with Jean-Christophe, what you said this morning, you use neural network to train the operator, right, to train observation operator. But if you cannot include this neural network in your optimization function, what you can do is you need to come back to use some ensemble methods, some sampling methods to approximate these gradients. But what if you can do that directly in PyTorch? That's what give a benefits that you can learn the operator and you can assimilate directly all these things together. Okay? So it's not only useful in the latent data assimilation, it's in any case, for example, you have your state, you have your observation, you don't know how to link them, you use a neural network, and once that's done, you can probably use the TorchDA package to help you how you're going to be able to perform data assimilation. And suppose 3D var, 4D var, ENK, like classic data assimilation algorithms. And this is a simple code snips. And basically, this optimization function already exists in PyTorch. Okay, so you can use all the so LBFGS, or use all the SGD at them as optimizer to help you solve these optimization problem. And here what I do is simply I create an interface between them. And you can set you can set either GPU or CPU to solve this problem. You can have the choose of different variables. And yeah, if you have needs, so please check our package. I think it could has a potential to be used in all the neural network surrogate model, neural network predictive model, etc. And yeah, so I'm happy that since the last year, I think we have this package open access. I get contact, and there's some of my collaborators that are working on different applications. So I will not name them all. But you can see really it's across the world, if I can say. And there are a lot of actually shared difficulties about the sparse observation, about non-explicit transformation function. You have to learn operator, etc. And yeah, I do believe that this can be used in a more wide scenario. Okay, yeah, so just come back to the air pollution. I'll be fast here. It's just to show you some tests. So here I'm using synthetic observations. I've also used the real observations, but the result will be less easy to interpret because real observations only get several points. You don't have the ground truth of the whole map. Okay, so here you can see which is your prior, and in some cases the prior and the truth you have a huge difference. Well, after correction, this is only based on 32 points that we have. In most of cases, especially in Central Paris, that we have quite a lot of observations, we can somehow quite good correct the prior error. There's some cases that's not that good. That's because in South or in North Paris, we have less observations. Okay, and as mentioned, this is a joint correction. So we correct NO2, we correct O3. And you see in the species that you have less observations, it works less good. But overall, it's not that bad, especially in Central Paris area. Okay, so yeah, actually, this the last slide before I go to more future work things. I've also done our proof of concept of that based on the weather bench data set, and you can see I have absolutely no observation point in the jaw potential. But thanks to the similarity or the correlation of that to, for example, temperature or humidity or the other species, even you don't have observations, but you have a joint co-assimilation system, right? And thanks to the observation network on the other variables, you can still somehow get a quite good correction. So you can see the posterior error, which is less good than temperature, which is normal because you observe directly, but overall it's quite reduced compared to the prior error. Okay, so finally some words about the OFML project and probably some other projects, because it's very ambitious, and yeah, I don't know yet what the other projects is. The idea is we want to have this end-to-end differentiable framework from the weather model to the physics-based model, and use this joint learning, as I mentioned, that couples generative AI and physics-based model, and also to have the fire control like fire redundant or fire break placement, and also this assimilation, all these in PyTorch, and to have really this end-to-end and unified framework to perform these things. And I do believe wildfire is one of the difficult, especially these kind of like regional wildfire spread prediction. It's a difficult task even for machine learning or neural network-based approach. So for the reason I already mentioned, and I do believe this is the field that we need more physics knowledge. But I think there may be better ways to do that by have a unified framework. And yeah, one last thing I would like to mention is I'm also involved in the PPR COTI project that's led by Florent Walleux at Montpellier. So the idea is we want to evaluate, so that's more for long term, to evaluate the wildfire risk in the whole France, okay? And the idea is to take random ignitions you have random ignitions at different places of France, and you try to see how your city, how your land will be impacted by that. And the advantage of we have something like PyTorchFire, either the current version, or we can integrate other physics-based model or rewrite with other physics-based model, is that it's very fast with GPU and can be calibrated, so we will be able to calibrate the model based on all the historical wildfire or recent wildfire in that region, okay? And you will have a best parameter at that region, and it will help you better to construct this risk of map. And this is the objective, at least for that work package in the PPR. Okay, so at the end, these are my collaborators. And Wenbo actually is the person who mainly developed the diffusion model. And now, in Wenbo and Abhishek, I succeeded in convincing them to move to NPC from Imperial College. So Wenbo is actually will continue working on the foundation or contractive model with me. So that's something quite similar to Homan, what you do. So please wait a little bit us, don't kill our game. So we have also Abhishek will start work on the wildfire, continue the PyTorchFire, and Zeyu was an intern at Imperial, and now he's at Virginia University. And with his supervisors, we try to collaborate to see if we can extend that to the UV fire with the human and wetland interactions. So the first test that's not very good. So we assume that we probably need more complex. So at least we need more parameters to be fine-tuned when we have a more complex geometries. And so the other collaborators. So continuous collaboration with Sandy Harrison, Rosella Akuchi, and also with Flo Hong and with Mark. So. And also thanks to the support from NVIDIA to give us a GPU. With this, I would like to thank you for your attention and happy to answer your questions. Thanks.